Good morning, good afternoon, and good evening, wherever you are. Again, I'd like to thank Gerald for the introduction and explaining our series. We have been doing this 101 series to help introduce some of the basics and then state-of-the-art in selected topics. This time we are going to focus on coatings, paints, and formulations. And again, I'd like to thank Park AFM Systems for this opportunity. I'm with Case Western Reserve University, a professor at Macromolecular Science Engineering Department. We primarily do things related to nanostructuring and surface chemistry, working with not only academic or research related work, but also development work with the industry. We do a lot of work at interfaces, modifying them with nanomaterials, nanostructuring, developing different patterning methods as well as sensing. On the other hand, with industry, we'd like to work with the toughest problems and challenging and opportunities where we can take the best of the basic platform from the university and apply it and make it relevant to the market. So in a way, we bridge this gap through this type of high performance cost ratioing and problem solving, where of course to fund the research we would like to work and collaborate with our industry partners. So today I'm going to explain to you about coats and paintings. So looking at the slides, you can say that when we refer to coatings or paint or protective coatings or even insulation materials, we can mean several things. We can mean architectural paint, industrial paint, anti-corrosion coatings that can be applied by simple brush, air spraying, thermal spraying, or baking in an oven, or different types of solventless deposition. So let's start with a common paint formulation. As you can see here, a common architectural paint will consist of a solvent, your carrier, a thickener, viscosity modifier, but then a lot of what constitutes a paint are some of the solid weight content, which includes pigments, different filler materials that gives it its body, cross-linkers, and then an important ingredient is the resin or the binder, which is in this case emulsion polymeride resin based on acrylates, styrene, or vinyl polymerized systems. And then you'd add things like coalescing solvents, biocides, etc. So a paint formulation can have between 20 to even 40 ingredients. So what does this tell you? Well, coating is a industrial venture that requires many ingredients to make it a successful commercial product. So some of the basics of a paint formulation means that you have to start with what questions. What is it that you want to desire in terms of properties for a paint? Gloss, anti-reflection, different types of non-fouling properties, okay? And then you have to start with a formula that you can then iterate or improve with different recipes at various ratios. And that is basically taking a formula that has been developed or is successful and modifying it slightly so that you can come out with a new and better product. So this type of iteration means that a paint formulation is actually a trade secret or something that is of value to the producer, in that they are working with suppliers and different types of um, mixing, packaging um, systems that allow them to sell and market a successful paint. Now, there are ways to quantify the composition. This can be based on pigment to binder ratio, pigment to volume concentration, and different types of uh, weights that can be associated with solid or volatile contents. A value called pigment volume concentration, for example, is simply the ratio of the pigment volume to the total volume of the solid coating. Thus, you can use this value to evaluate the effective concentration of each pigment in order to get the minimum property that is desired. Okay. Other properties like the critical pigment volume concentration, which is the PVC at which the binder concentration is barely sufficient to completely wet pigments and fillers, allows you to determine the economics of the formulation. In other words, in any formulation, you want to meet what we call the minimum percolation threshold to a desirable property, such that you save on the cost of the ingredients. Okay, and so you can use this to monitor properties like hardness, flexibility, gloss, etc. of every ingredient or pigment that you add. Other types of numbers that are useful for determining a paint performance would be the oil adsorption value, the specific surface area or BET, okay? And this type of values again allow you to approximate or determine the stability and the diffusion properties of paint. So basically, there is art, but there's also a lot of science that can be gleaned from the development of paint. Here, for example, you can see how different ingredients, such as your pigments, your soluble dyes, can move a property, whether we are referring to the hiding power, the brilliance, and then controlling its ability to prevent flocculation or ability to disperse, can vary between a opacifying pigment and a soluble organic dye. So opacifying pigments are typically solids or particles. On the other hand, soluble organic dyes are organic small molecules that are added to, let's say, provide color. So let's start talking polymers here. What are the different polymer resins used for describing paint? Okay, so when we say epoxy paint or epoxy coating, we are referring to the chemistry of reacting a epoxy functional group, which could be attached to a bisphenol A epichlorohydrin polymerized resin, or it could be a polyester, a polyethylene oxide, a PMMA backbone, which has an epoxy group. And of course, those who have worked with epoxy paints means that along with the epoxy, you need a hardener. A hardener, usually an amine, that provides the cross-linking to produce a thermoset paint that is a protective type of coating. Other types of polymers could be based on the polyesters or polyurethane. Again, polyurethane can be a thermoset or it can be elastomeric based on the hard and soft pigments or rather ingredients. And then you can vary the polyurethane chemistry by changing the polyol or the isocyanate type of ingredient. Silicone pretty much describes protective coatings based on siloxane chemistry. And of course, the most common type of architectural paint includes polyacrylates, styrenic types of, or polyvinyl acetate type of polymers or copolymers that are used as binders that is produced using emulsion polymerization. So let's first define some terms here in order to proceed with other discussions on the basics of paint. So when we refer to finish, it could be gloss or matte, and you generally refer to that as satin, shiny, or flat finish. A paint can be classified as oil or water-based. Oil can be substituted with the word solvent. Solvent-based paints are minimized these days because of environmental reasons, but they are very effective still in using paints for a protective function or different types of finishes. On the other hand, majority of what you will buy in a paint store these days are water-based, meaning they are basically formulated from emulsions in a water-based solvent with different additives and ingredients. The term thinner refers to a solvent that is used to thin or control the viscosity of paint. But in many cases, a thinner is not necessary. If not, in fact, it is not good to thin a paint before using it because a paint is usually optimized with the right viscosity when you first apply it. Now, other types of coating methods, which we will review as well in this time together, includes thermal spray, powder coatings, plasma treatment, different type of solventless coating methods. How about pigments? What do we mean by pigment? Well, a pigment is basically a granular material or even a powder material that is used to control or contribute to the texture, the color, the toughness, the opacity of paint. Okay, so pigment could refer to silica, calcium carbonate, clay, other types of carbon-based materials that are used to add that function. What we refer to as hiding pigments is quite specific. They basically provide the opacity of paint. Typically, they are based on titanium dioxide. But if you have heard of lead being used in paint, that was the function of lead before. It was to give it a hiding power. But as you know, lead is quite toxic and is not used today, but is found in old paint. Okay, and so the main hiding pigment that is used is either based on titanium dioxide or what we call core shell polymers, which also produces that opacity effect. If you're thinking about color, color can come from organic dyes or inorganic dyes, and of course, the ability to control the right intensity, the right brightness is important in architectural paints, and there's a whole science here that involves computing as well as looking at the correct intensity and brightness of different light conditions of various color pigments. So I will not have time to go through that, but just to let you know, there's a science that governs the right choice of color pigments. Other terms, so filler. Filler is usually used to control the viscosity or thicken the film, and this has to be as economical as possible. This could be based on talc, diatomaceous earth, calcium carbonate, and so on. Okay. Then we discussed about titanium dioxide, so I won't repeat those statements. But how do they look like? Well, as I mentioned, they are powders. They can be in the form of micron-sized material or even nanometer-sized materials, as shown in this SEM micrograph of various SEM and TEM micrographs of various filler materials. That includes diatomaceous earth, so you can see this interesting structure, which are basically remains of different types of marine animals that are harvested on sand. All right, the term binder, what do we mean by this? Binder is basically the vehicle that forms the film, a component of the paint that promotes adhesion, forms the type of finish, as well as providing the structural stability of a film coating. Now, this can go by another term. It could mean resin. So binder could be interchangeably used with resin, the term resin. And another term that I can emphasize here is usually when you refer to binder, it refers to a polymer. So that polymer can be acrylic, polyurethane, polyester, other types of resins based on phenol, formaldehyde, melamine, epoxy, etc. Okay. Here you can see that a binder, which then forms a film, is governed by either solvent evaporation, cross-linking, or even catalyzed polymerization. Essentially, the film, or as the solvent dries out, a uniform film is formed, shown here dramatically by these colloidal particles that then pack very well. In this case, a hexagonally packed a colloidal particle, which then results in diffusion of the polymer chains to form a uniform film. Okay, so binder is very important, essentially, in film or coating formation. Now, what we hear the term latex or latex paint is essentially the particle binders that are produced by emulsion polymerization. And usually these are stabilized in the presence of surfactants or even other types of colloidal dispersion methods. And they can be cured if you have alkyd or reactive functional groups or acrylates that can either be thermally or even photochemically cured to provide a more uniform or tight film. So again, these are pictures that shows the presence of colloidal particles in film formation. Maybe more dramatically, as shown here, latex film basically drives formation of this packed structure where the solvent evaporation and hence different solvents or water evaporation provides a highly packed structure, which then results in diffusion of the polymers within these colloids to form a film, a continuous film that protects or covers the coating. This process, as you can see here, involves coalescence. So first, as the solvent evaporates, the particles aggregate, and then as they aggregate, further solvent evaporation results in coalescence, and finally, diffusion of polymers to form a continuous or contiguous film. Now, let's talk about solvents. Solvents, again, are divided between oil or organic solvent-based as well as water or aqueous-based coatings. One of the things you can say about solvents is that they control the viscosity as well, or you can dilute them using a thinner. But then solvent-based paint means that you can have combinations of aromatics, alcohol, ketones, various types of petroleum distillates to produce a film, or rather a paint coating, which involves evaporation of that organic solvent to form a continuous film. Now, there's a lot of concern these days on volatile organic components. So for sure, a paint that smells includes volatile organic compounds, including the solvent that gives it a uncomfortable smell or feeling when you have a newly finished paint, okay, procedure. So more and more countries in Europe and other countries, and including the direction in the US, not only discourages but even prohibits the use of organic-based paints. That is why um, there's a lot of move towards solvent-less or powder-based coatings or even water-based coatings. Here you can see the rheology of paint, which is governed by the time. So basically the viscosity increases as you evaporate the material, the solvent from the film. On the other hand, the rheology is quite important when you're applying the coating on gravity driven processes such as walls versus flat flooring or coating without the influence of gravity. Now, additives. Additives is a general term that is used to describe other components of a paint formula that provides color, controls foam formation, surface tension, use of catalysts to accelerate curing, emulsifiers, UV light stabilizers, biocides that can control bacterial growth on the formulation, and so on. Okay, so as I said, a typical paint can have anywhere between 20 to 40 components before it sees the package that is eventually used by the consumer. So let's give a general talk about the properties of paints. So when we describe thickening, we are basically talking about the rheology of paint. Rheology modifiers are added to paint in order to control its viscosity. Basically, it's what we call a thixotropic material. A paint, once applied, should not flow freely, especially on the vertical wall. It should hold its place and then finally dry. So the control of rheology on paint is quite critical, especially if a paint is left for a long time under storage. And when the user is ready to use the paint, the viscosity has to be controlled. So a rheology modifier, obviously you need a viscometer or rheometer to understand the flow behavior of paint. It can be optimized either by the use of the proper modifier or even concentration or dilution. Now, let's specifically talk about polymer and its control on pigment dispersion. So as shown here, a typical polymer binder or particle associates or aggregates in order to form the paint constitution. Now, what is not good is, for example, to have unwanted aggregation, which gives the paint its inhomogeneity. So sometimes they have to add dispersing agents, including polymers and surfactants, in order to keep the paint particles from forming aggregates or coalescing early on as a formulation. Okay, so homogeneous dispersion is quite important property to achieve in any formulation. So why do pigments need to be dispersed or properly homogenized? It's because of the term phase separation. Okay, solids like to separate from liquids. Oil and water tends to separate or phase separate because of differences in hydrophobicity or polarity. The same with pigments. Pigments are essentially solids that tend to aggregate or phase separate with the medium, the solvent, or the binder. And therefore, dispersing them is important for achieving the right percolation threshold or minimizing the amount of ingredient, but still achieving the same property. So as shown here, through the years, there have been many ways to control the dispersion of paints, pigments, and binders. One of the things that have been used are what we call HEUR and HASE type of controlled association for particles. So hydrophobic ethoxylated urethane means you have a amphiphilic or a hydrophilic association that controls that dispersion. Another term, hydrophobically modified alkali soluble emulsion, again makes use of ingredients based on um, molecular design that gives it a associative or um, controlled association properties between the surfactants and the pigments. Okay, so this is an additive that's special in stabilizing the material. So we're talking about here about rheology, so I might as well introduce some basic terms. Rheology is, of course, a measure of flow behavior uh, per unit area, or the force it takes to move per unit area. And this is looking at a property based on modulus or viscoelastic behavior under controlled shear rates or shear stress. So what might be familiar to you is looking at the stress versus strain, stress versus shear rate behavior of various fluids. For example, water is associated as Newtonian, and the rest are, as you see in this curve here, are what we call non-Newtonian fluids. Either it's pseudoplastic or dilatant or Bingham. Bingham means you need to achieve a constant stress, and then flow begins at that particular constant. And then other non-Newtonian fluids, for example, paper, pulp, grease, paint, are considered pseudoplastic. On the other hand, beach sand or starch in water is an example of what we call dilatant behavior. Another property of paint, of course, is adhesion. So adhesion is the tendency of certain similar molecules or phases to cling together. On the other hand, the term cohesion means the interaction between similar molecules. So adhesion is a term which both has a physical and chemical component in promoting adhesion. And these mechanisms are used to improve, let's say, a paint that has been coated on a wall surface, which emphasizes the point with regards to coating. Coating is only as good as your surface preparation. So do not forget to clean a surface before you do some painting. Here you can see some fracturing tests that can measure cohesive or adhesive strength. Basically debonding. So two surfaces where you have a adhesive material sandwiched in between them can be characterized in terms of their fracturing behavior as shown here. And there are ASTM or ISO tests that can be associated with any of these techniques, including in-plane shear and out-of-plane shearing methods of testing adhesion. As I said, there are several mechanisms for adhesion, physical and chemical. So mechanical adhesion, meaning interlocking of various surfaces. And a good term here could be the Velcro approach in adhesion. Chemical adhesion means that you have non-covalent forces or the formation of covalent bonds that result in very strong binding or adsorption. Dispersive adhesion could be weaker forces or dispersion forces that promote adhesion. Electrostatic adhesion can be based on charge attraction versus charge repulsion. And then diffusion behavior could mean that a material, simply because it flows between two planes, means that you have a continuous attraction between those planes as long as the diffusive behavior of that adhesive material goes into place. Now, basic to adhesion, of course, is differences in surface energy. And the term hydrophobic, superhydrophobic, hydrophilic is associated with wetting behavior with water. So in this very basic formula called de Young's equation, allows you to measure the surface tension difference between the air, water, water, solid, and solid air interfaces, which is governed by this cosine theta. So the lower the cosine theta value, the more the liquid or adhesive wets the surface. The higher the cosine theta, the more it hates the surface or prevents it from wetting. Okay, so this is a very basic term that is being used to characterize the interaction of surfaces with its environment as well. Now, let me describe here terms referring to protective coatings. So differentiating protective coatings from architectural coatings. Architectural coatings are usually applied in the interior or inside the house, and they're used to give texture, color, etc., without a protective function. On the other hand, light industrial, or even extreme environments such as pipes or in the platform for oil and gas extraction means that we want to prevent environmental damage, mainly through corrosion. And so different types of polymers have been used as protective coatings. They can be based on epoxy, phenol formaldehyde, phenolic, polyurethane, or even the use of other types of fluoropolymers or high-performance polymers that produces basically a protective barrier or a thin film, or what I call hermetic sealing, that prevents diffusion of the corrodant, which could be oxygen or moisture, through that barrier and then preventing it from getting to the carbon steel surface or the steel surface that you're trying to protect. So this list here is not exhaustive, but just gives you a representation that protective coatings are tougher materials, more expensive than your typical acrylate, polyurethane, or even polyester resin. Additives are sometimes used to improve the resistance against coating. So other than providing a barrier material, things like zinc, organic, inorganic salts, silanes are used to prevent diffusion or control the electrochemistry such that before the carbon steel is reached, let's say a sacrificial anode or sacrificial material like zinc is consumed, or a silane agent basically reacts with water, or other types of salts reacts with water to form an oxide that then serves as an additional preventive layer. Okay, so this type of properties are basically to prevent rusting, which is, by the way, a very important part of our economy. It's been said that as much as 5% of the economy of any industrial country is affected by corrosion. Okay, and there's a big, big industry focus, commercial focus, just on preventing corrosion alone. Now, I think we can go fast through this major paint and coating material. So I'll just explain more when we talk about polyacrylates, polyurethanes, polyesters, resin, epoxy oils. This is the chemistry involved. So acrylate paints are made by vinyl polymerization in emulsion to produce different types of water-based paints or latexes, which have formulations based on the vinyl monomer. So here it just gives you an example of some of those vinyl monomers. It could be methacrylic acid, vinyl acetate, it could be methyl methacrylate, okay, and other cross-linkers. And these are made by emulsion polymerization. So in emulsion polymerization, you basically have an oil and water phase stabilized by a surfactant. And then for emulsion polymerization to take place, you need to have an initiator. Typically, this initiator is introduced from the aqueous phase. And then as a micelle is formed and the polymerization takes place inside that micelle, the monomer is depleted from the emulsion or the oil phase and transferred towards the growing particle. Okay, so unfortunately I do not have much time to explain this emulsion process, except that you can classify them, let's say, into stages, stage 1, stage 2, and stage 3, which is looking at the population of the micelle as well as the decrease in the monomer concentration. So decrease in the monomer concentration means you have conversion towards a polymer. And as I said, the polymerization takes place actually in a micelle, where you have your initiator producing the polymer, growing the polymer as a particle protected by the micelle. And then as the monomer coming from the oil phase is depleted, this micelle or this particle will just grow and grow until they form a latex particle. Now, epoxy. As mentioned, epoxy is basically the epoxide group that reacts with a amine or diamine, as shown in this reaction, forming a ring-opened procedure that then cross-links to produce a high modulus, high-strength coating or material. So epoxy resins are the most dominant, if not the most cost-effective for a lot of applications in many industries, including the oil and gas industry. So you can see here, epoxy-based paint can be applied against highly weathered conditions or even underneath or undersea operations or below the tide, and has been used effectively in many types of industrial coatings as well. Alkyd coatings are oil-based paint. Typically, you have control on the chemistry of the alkyd together with other components such as polyesters and vegetable oils. This type of paint is still useful, has many uses for finishing and architectural or gloss finishes, but it's not in the same volume as you would find, let's say, with acrylic or other types of paint formulations. What we term polyurethane can be a two-part system, or it can be in terms of dispersions of pigments. The polyurethane chemistry starts from reaction of a polyol or a diol with a diisocyanate functional group to produce a urethane or even urea material in the presence of water and CO2. Okay, so there's a lot of chemistry that refers to polyurethane, polyaspartic acid, polyurea that is quite similar. A polyester is based on the reaction of a diol and a diacid. Polyesters are quite useful, a very good combination of properties that resist corrosion as well as chemical resistance. So overall, it's competitive to polyurethane in some formulations. Fluoropolymer is a more expensive material. Obviously, the famous polymer there is based on Teflon, okay? And here you can see Teflon, fluoroelastomers, different types of fluoropolymers based on PVK, PVDF, polyvinylidene fluoride, or other copolymers being used predominantly as highly effective protective coatings, very good weatherability, and chemical resistance. And as you can see here, nuts, bolts, surfaces that are protected with fluoropolymers have very high durability when it comes to coatings. So you can expect them to be more expensive than your typical formulations. And they can be prepared either as dispersions in a solvent or powder coated. Fluoropolymer-based latex paints are actually dispersions of materials like PVDF, surfactants, and other resins that can produce a formulation where you can you can first coat them on a surface and then bake them, or high temperature curing provides the final process to give you a good finish and protective function. Okay. So again, PVDF is a more expensive coating material, but very effective when combined with latex ingredients or binders. Now, I'm almost done here. Let me just finish by citing what are some of the desirable properties and applications for a coating. So first is a coating will be good if you have an antimicrobial property. This can be achieved by either adding some antimicrobial agents, including silver ions, silver particles, betanes, sulfobetanes, or even photocatalytic titanium particles. Okay, and that means that you're able to add that antimicrobial property, let's say in a architectural paint that is useful in hospitals. Okay? Anti-scratch coatings. If you have an automotive application, of course, preventing scratch, preventing abrasion, increasing the weathering means that you need to have a smart coating that heals or even prevents scratching because of the hardness and the adhesion that you build with it. So self-healing paint here, for example, is an interesting concept where you have autonomic healing or release of monomers that then produces a toughened seal or cures the crack or scratch on any automotive finish. Clay nanoparticles have been used to increase weatherability, mechanical properties, preventing diffusion, or even control rheology. So clay particles. What differentiates clay for a particle from a typical clay nanoparticle is that you can do a lot of intercalation chemistry and control of dispersion or nanostructuring because of the high surface to volume advantage of a nanoparticle. It would be nice to have what we call an anti-graffiti paint. So a paint that is not easily damaged or sprayed with a paint that needs to be cleaned later. So any anti-graffiti coating tends to have properties that are self-cleaning, super hydrophobic, or very low adhesion to most common paint solvents and carriers, okay? Or even self-cleaning, meaning during rain or oxidation, the graffiti disappears. Heat-resistant paint means you can use this paint even at extreme conditions. The paint could be used in rooftops or walls or different high-temperature environments such as the desert, and then they maintain their property. Fire-resistant paint means structures that need to be protected from flammability, and this typically involves adding more inorganic additives or even amphiphilic particles based on phosphoesters, boronate, or melamine to improve that combustion prevention. Anti-icing coatings means that ice does not easily form. It could be based on super hydrophobic effect or simply surfaces that prevent ice crystal formation. Anti-corrosion coatings, as I mentioned, comes from additives or protective sealant behavior that prevents the corrodant from entering the surface. So basically, a steel surface is always amenable to oxidation in the presence of water and oxygen, forming rust. Other types of ingredients for preventing resistance, for example, involves the use of conducting polymers, as shown here. Antibacterial, anti-mold coatings, color-changing paints, electrochromic, thermochromic, photochromic paints, or smart paints that can change with stimuli-responsive field effects are quite interesting because they can provide various aesthetic effects as well as functional effects for controlling color. So for example, as shown here, based on temperature, one can control the color, or based on transmission, with specific heat activation, you can have high or low transmission. And of course, I'm not just referring here to one single coating, but it could be multi-layer coatings that provide that function. Bio-based paints, you have ingredients based from sustainable materials or ingredients based on bio-derived things like polyols from soybean to make your polyurethanes, or ingredients derived from making polyesters like polylactic acid or even cellulose. Increasing those components in paint products is always a goal when you want to have more bio-based feedstocks used in the production. So actually with that, I'm ready to finish. I hope this time with you has been productive and you've learned this last 45 minutes more about paints than you normally would. So with that, I'd like to thank you, and I'll be happy to answer any questions, or you can email me using my email address. Thank you.